Hi, my name is Paul D. Williams, and I'll be presenting the surface chemistry of single molecule barium detecting fluorophores in differing media. To start, in a radioactive process called double beta decay, occurs when two protons spontaneously convert into two neutrons. This will release two electrons and two neutrinos. In a different, mathematically proven process that has never been seen experimentally, the neutrinos are self-annihilated prior to ejection in a process called neutrinoless beta decay. This will create two highly charged electrons that will be shot out at a different velocity. This can be measured with a time projection chamber, and using 1/2 mv squared, we can find the kinetic energy. Model reaction of this process is the decay of xenon into barium 2 plus ion, which can be detected with fluorescent sensors. Previously, we have gotten highly selective barium ion detecting with fluorescence microscopy using fluorophores such as naphthalomide or Verdipi. An issue is the fluorophores are too close together, and these will quench each other or decrease the fluorescence intensity. To combat this, we will make these long chain monomers that are able to create more space in between the fluorophores that hypothetically should reduce the quenching effects. Also, they are used to test the mobility of the ions. Some may make them move faster, some slower, some may make the ions come to a complete stop on the surfaces. We have three different types: an alkyl with hydrophobic interactions, an ether with some electron donating potential, and then a highly electronegative polyfluorinated compound. For the synthesis, we'll start with 10-bromodecanoic acid and protect it with the methylation. To make the ether, we'll react it with triethylene glycol and then deprotect with lithium hydroxide. In an alternative reaction, we'll use that same 10-bromodecanoic acid that's protected and react that with perfluorooctanoyl chloride and then deprotect it with lithium hydroxide again. For the Bodepi synthesis, one of our fluorophores will start with 2,4-dimethylpyrrole and 4-fluorobenzaldehyde and TFA. Then we'll use DDQ to oxidize one of the amines before the use of boron trifluoride etherate to give us boron dipyrromethane or Bodepi. For naphthalomide synthesis, another fluorophore will use 4-bromo-1,8 naphthalamic anhydride and N-butylamine to create a less reactive tertiary amine. Then we'll use 12-aminolauric acid and NHS to bind to the glass slide for our dry phase studies. Within those dry phase studies, we imagine that the fluorophores and the monomers will order themselves on the slide similar to the figure below. In a liquid phase study that we test with just the alkyl monomers, we imagine that they'll have less order within their arrangement. We plan to use an intermediate viscous media to understand and bridge the gap between the liquid and the dry phase. For our future work, we plan on making an amine ion transport model starting with the dipeptide glycine. We plan to cleave off the carbonyls and then add to 10-bromodecanoic acid similar to the other reactions. For our viscous media studies, we plan to use low molecular weight polyethylene glycol, polyethylenamine, and some polyfluorinated polyethylene to do those tests with titrating the fluorophores in. Next, we have this highly selective 18 crown 6 that reacts the complexes specific heavy metals that can be used for barium ion detection. On the left here, you'll see the single molecule fluorescent imaging, where each dot is an ion of barium. In conclusion, our lab has synthesized several monomers and fluorophores that have been used in different phase studies. We hypothesize that the use of these monomers will decrease quenching in single ions detection. We would like to thank our collaborator, Dr. Marvin Jones, NSF, Welsh Foundation, and Next Collaboration. Thank you.